There's one other bit. I didn't really derive the E equals MC squared. That does pretty much require calculus. There's several different versions of E equal MC squared. Matter of fact, as I'm doing this, I'm thinking, wait a second, I skipped a couple things from relativity. Because the last thing we did with relativity, we did the Lorentz transformations. I'll finish this up and maybe Thursday we'll drop back to a little relativity again. So Lorentz transformations. The mass, the apparent mass of an object is equal to gamma n sub naught. We'll call gamma is the Lorentz factor. N sub naught is the rest mass, in other words, the mass of an object when it is at rest relative to the observer. Now this equation right up here that mass is equal to gamma times n sub naught, not every physicist will agree with that. Because some will make the claim that it's not the mass that changes, because as you get closer and closer to the speed of light, this gamma gets bigger and bigger. And so mass is equal to gamma times, so the mass would get bigger and bigger. Some physicists claim that it's not the mass that gets bigger, but it's really the momentum. And that properly it should be that the momentum is equal to gamma times. Seems kind of odd, because if really a rest momentum would be zero. And I did read in one source that it depends upon when you were taught, or by who you were taught. So, for better or for worse, I go with the mass increasing. I've talked to other physicists and talked about, hey, something gets bigger, the mass increases. And I mean, there was no look of pity in this person's eyes. So there was a video a student brought to my attention last year, I think it was, questioning E equals MC squared. And it all came down to this. He was young enough that he was going, it's the momentum that changes, not the mass. So I bring that up. That's what I'm doing, just in case you run across a video that says, no, that's not true. It's the momentum that will suddenly blossom and not the mass itself. Personally, I've not run into a case where it made a difference. So n equals mc squared, this is actually the end result of it. There are various incarnations of the derivation, but one of them is the previous line is e squared is equal to m squared c to the fourth, which means that e equals plus or minus mc squared. And physicists looked at it at the time and said, well, the negative doesn't make any physical sense, and so e equals mc squared. Later on, some physicists said, wait a second, suppose the minus sign does make sense. Let's come up with a whole bunch of physics, assuming that's true. And it turned out that's the essence of antimatter. So it turned out to have some physical sense after all. Another form of this is that E squared is equal to P squared C squared plus M naught squared C to the fourth. Notice the difference here. This is the relativistic mass. This is the rest mass. So if you're talking about light, which doesn't really have a rest mass, so if light, this term drops out, and you're left with E equals PC. That light itself has some sort of momentum equivalent. So if we do that, HF would also be equal to VC. And so the momentum of light would be HF over C. Because if I'm doing conservation momentum with light coming in, acting like a particle, I've got to have some formula for momentum. So what we're going to do is we're going to simplify our drawing here. I have light coming in at some frequency, an electron at rest. Yes, I know electrons aren't really at rest, but if we compare it to the speed of light, it's close enough. The electron is going to shooting off, and then light is going to have to lose energy because it gave some to the electron, and I drew it better than I did over there. It comes in with a much higher frequency and leaves with a lower frequency. Or in terms of wavelength, it comes in with a shorter wavelength and leaves with a longer wavelength. So this comes in with some initial energy and some initial momentum. The electron, the momentum of the electron initially is 0, close enough. And then the electron has some BE final. And this is the energy of the light final at some momentum of the light final. Questions to hear?
Did you just draw a dotted line there for like demonstrating like an angle or something?
Yeah.
Okay.
Yeah, pretty much. Just to keep in sync with it, I'm going to call this angle theta. Now, I know if momentum is conserved, momentum is a vector, even though I didn't draw the vector symbols because as you get further on, you get sloppier in some notation and more picky about others. So my initial momentum is the momentum of the light. It's a vector that I have drawn in that direction. And I don't think we'll need, we probably will at some point. Let's go ahead and define I hat and J hat. So this is the initial momentum of the light, which, as we have written over there, is h times the initial frequency of the light divided by the speed of light. Afterwards, I have things going in two different directions. I know the sum of the initial momentum must equal the sum of the finals. So I have, this is h f final, but this is of the light, over c. And this would be mass of the electron times the velocity final of the electron. And that angle there is theta. And I could drop, I'm going to drop this subscript here. This is just I'm not worrying about relativistic effects here, so the difference between M and M is not of critical importance. And the speed of light is going to be c, so if I see a v here, that's of the electron afterwards. Since the electron's at rest beforehand, I have only one v. It's the electron final. You're uncomfortable with that? You want me to put subscripts in, or you're just feeling overwhelmed?
Can you explain again the different, because you're looking at these as vectors, yeah?
Yes.
Okay, can you explain again?
The triangle?
Yeah, my brain is wanting to connect it to that over there specifically, like I see theta, but
Before, I have momentum of the light. This is gonna be the momentum of the light initial plus the momentum of the electron initial.
yes.
Given our scale here, the speed of the electron is close enough to zero that we don't worry about it. So all the total beforehand is just whatever the momentum of the electron is beforehand, and it's, or sorry, momentum of the light beforehand, and it's going in that direction.
Okay.
Afterwards, I have two objects. I got one shooting down in the fourth quadrant, one in the first quadrant. So I've got this, which is the momentum of the electron final, and this, which is the momentum of the light final. Under conservation momentum, the total momentum beforehand equals the total afterwards. So it's this plus zero. And when I'm adding light, and when I'm adding vectors head to tail, I went that one first because that angle I define as theta. And then now I'm here, I go off in that direction. So this is P gamma final, P electron final. And the sum of vectors is a vector from where you get to where you end.
Yeah, is it, in these cases, is it more typical for the, defined angle theta to be the one that is in relation to the light
Yes.
instead of the electron? Okay.
Yeah, the typical.
That makes sense. Thank you.
Yep. Other questions? All right. Law of cosines. If I've got alpha, beta, gamma, let's see. Someone want to take a shot at telling me what the law of cosines is for any of it? Okay. Law of cosines is the more general form of the Pythagorean theorem. So if we take an angle and set it to 90 degrees, we could get the Pythagorean theorem from it. I was hoping that would help. There.
No.
I heard an there. And it's like,
I said but never mind. I lack confidence.
Okay.
Yeah,
Your spinal cord.
I'm not good at following the law, so.
All right, so a squared plus b squared. So if that is 90 degrees, so if gamma is 90 degrees, then we have a squared plus b squared equals c squared. Law of cosines, I have c squared is equal to a squared plus b squared. So it looks like Pythagorean theorem to start with, minus 2ab cosine of the angle opposite of that, which is gamma. So if gamma is 90 degrees, cosine of 90 degrees is 0, that whole term drops out and we get the Pythagorean theorem. This also allows us to do anything. I could do a squared, it's going to be the sum of the other two squared, minus 2 times the other two cosine of the angle opposite a. And the last one would be b squared is equal to a squared plus c squared minus 2ac cosine of beta.
I remember these now.
Yeah.
I've talked to them in January.
Good times. hopefully some fond memories flooding back.
Yeah, obvious.
If I apply that to this, since I have only one angle defined here, I have mv squared equals hf gamma initial over c squared plus hf gamma final over c squared minus 2 times hf gamma I over c times hf gamma final over c cosine of theta.
Okay. Don't let me say anything else.
Leave it there for right now.
Yeah. Okay, catch up.
Okay.
How'd you break that back quick?
Well, I was following a little bit at the beginning, and I fell off.
Here we go. Let's simplify it some. Do I keep it as NV? I keep it as NV. So mass of the electron times the final speed of the electron squared equals h squared f gamma initial squared over c squared. All I'm doing is just square multiplying the stuff that is in there. H squared h gamma final squared over c squared minus 2h squared f gamma initial f gamma final over c squared cosine of theta. Quick check to make sure I didn't make no errors somewhere. Now, I know that the frequency of the light drops. The reason I know this is that the energy of the light, the light has to give up some energy to the electron. If energy is conserved, light comes in with a certain amount of energy. If some goes to the electron, there's less left behind for the light. So F gamma final would be equal to F gamma initial plus some change in frequency. Do I need to wait a minute? So I'm now going to take this and pop that into there, into my final. That way I'm dealing, the only F with a subscript is going to be the initial frequency, and then I've got this, whatever the change in frequency is. So mv squared is equal to h squared f gamma initial squared over c squared plus h squared times f gamma initial plus delta f squared over c squared minus 2h squared f gamma initial times f gamma initial minus delta f over c squared cosine of theta. Just double substitution at this point. I'm now going to make one other shortcut. At this point, I'm going to make f gamma initial just be f initial. Just so that there's fewer subscripts to write. So MV squared, quantity squared, is equal to, well, I can factor out H squared and C squared, so let's just H squared over C squared times F initial squared plus, this would be F initial squared plus 2F initial delta F plus delta F squared minus 2F initial squared minus F initial delta F. Cosine of theta. And then another quick check to see if I did cut us there somewhere. Squared, C squared, got factored out. Oh, okay. It's still just the conservation of momentum equation. Conservation of momentum.
Dr. Fox.
Yes.
The delta F's, I'm just tripped up about all the delta F's. Could you go through why that delta F is next to the 2F initial and then the plus the